almost daily reports that black holes have been found. Has anybody actually found a black hole?
The answer to that is no. No one has ever found a black hole. There are two characteristics that are alleged for these black holes, and one is an event horizon and a singularity, and no one has ever found either one of them. And the other thing is that the true definition of black hole universe is that it contains only one mass, and that's the black hole itself. So you can't have multiple black holes. So consequently, no one can say that there are black holes all over the universe. And so they can't find any because there's nothing to find.
You say that there are different types of black hole universes and Big Bang universes, and they can't coexist. What does that mean?
Well, there are 4 different types of black holes that have been alleged in theory, and I can list them for you quickly. It's non-rotating charge neutral, non-rotating charged, rotating charge neutral, and rotating charged. So there are 4 types. Sizes don't matter. And then there are 3 types of Big Bangs. One is a spatially finite universe that's expanding, and the other 2 are spatially infinite universes of different characteristics, and they're expanding. And so, by their very definitions, they can't coexist because, let's take for example, black hole universes are all eternal, but all Big Bang universes are of a finite age. And so, similarly, black hole universes are spatially infinite, but we have the 3 Big Bang universes. One is finite and 2 are infinite in a different characteristic. So they can't coexist by definition. So when you hear a person talk about black holes and Big Bangs together, they never specify what type of Big Bang and what type of black hole. They always just say Big Bang, black hole. Well, this doesn't tell us anything. And the other thing is, as I pointed out, they can't coexist by their very definition, so it doesn't make any sense.
Scientists tell us that they have found a radiation relic of a Big Bang in a cosmic microwave background. Where does this radiation come from?
The idea of the scientists propose is that this Big Bang radiation in microwaves is a relic of the early stages of the universe from their Big Bang theory, and they carry out a number of experiments to detect this radiation. However, they've never proven that this radiation comes from space. The truth of the matter is, if you put a glass of water in a microwave oven and turn it on, what happens to the water? Anybody who's used a microwave oven knows that the water gets hot, and it does so by absorbing microwaves. So that means water is also an emitter of microwaves. Well, when we consider this very simple truth, we know that the surface of the Earth is mostly covered 70% by water, and there's water in the atmosphere all the time. And in steady state conditions, we have microwave radiation throughout the atmosphere. And the most distant detection of the microwave, so-called microwave background, of the mean temperature of the universe that they tell us, has been at an altitude of 900 kilometers with a satellite that could not protect itself from microwaves. So the truth is that the microwave detection for the temperature of the universe is actually microwave signals from water on Earth. It does not come from the cosmos.
Okay, thanks for the interview.
Thank you very much. I'd like to first begin by dedicating this to my brother, J Crothers, who died in 2008. And the first thing I'd like to point out to you is that you might not be aware of it, but there are more than one type of black hole. When you hear a proponent of black holes and Big Bangs talk about them, do they ever tell you what kind of black hole and in what kind of Big Bang universe? Never. They seem to be even unaware of it themselves, that they have 4 types of black holes and 3 types of Big Bang universes. Let's run through them very quickly. We have non-rotating charged neutral, so-called Schwarzschild black holes. Then we have non-rotating but charged black holes. These are called Reisner and Nordstrom black holes. Then we have rotating charged neutral. This is a Kerr black hole. And finally, rotating charged black holes. This is a Kerr-Newman black hole. But with Big Bangs, we have 3 different types. And it all depends on this strange thing here called K. It's called a curvature, a constant curvature. That's what we'll say about it. And it tells you which one is which. Well, if we have K equals -1, we have a negatively curved space-time with spatially infinite and expanding. If we have K equals 0, we have a flat space-time, which is spatially infinite and expanding. Now we have K equals 1, this is positively curved space-time, it's spatially finite, expanding and later contracting. So I pose to you again, when a proponent of black holes and big bangs says anything about this, do they ever tell you which one they're combining with which? Never. Why? They don't seem to know. But without specifying what black hole in what big bang universe, they're not telling you much. Right? So let's have a look at what they actually do here. But before so, the first thing is, let's compare all types of black holes, the 4 types. Now I'll point out quickly that the sizes of black holes don't matter. We're all certain types of human beings. There are races of man. I'm a Caucasian. Probably most of you are. Some of you might not be. But that's a type of a human being. But small or big, I'm small. But I'm still a Caucasian human being. Well, black holes, size-wise doesn't matter either. They say that there are micro black holes, mini black holes, intermediate black holes, supermassive black holes, ultra supermassive black holes, and now they're telling us we have obese black holes. I don't know where they're going to stop. They don't seem to stop. They just keep adding adjectives, and that makes bigger and bigger black holes. But the fact of the matter is they're all only of these 4 types. Now let's compare the black holes to big bangs. All types of black hole universes are spatially infinite. We go to the big bangs. Well, one of them is spatially finite, and the other 2 are spatially infinite, and there are 2 different types of infinity. Do they match? No. Let's have a look at this one. All black hole universes are eternal. Technical terms are static or stationary, but they're eternal. Well, every one of the big bangs that are alleged are of a finite age. How old? Well, they tell us maybe it's about 13.8 billion years. But does that match? No. Black hole universes, well, they actually only contain one mass. I'll talk about that a bit later. And we can compare it with big bangs. They're supposed to contain radiation and many masses, including black holes. But that doesn't match. No black hole universe is expanding. All black hole universes are not expanding. But all big bang universes are expanding, except the finite one. That might contract. We don't know when, but maybe. And finally, this is a little bit of a technical term, all black hole universes are asymptotically flat, or asymptotically fat, they could be, asymptotically flat, or asymptotically curved. And all big bang universes are not asymptotically anything. So does that match? No. Well, we've got 5 mismatches here, and these are all generic characteristics of these different universes. And I'll point out also, we saw in the last slide, a K curvature. Well, notice that no black hole universe possesses a Big Bang constant K curvature. That's another big difference. Well, that's what defines the 3 different Big Bangs. It's got nothing to do with black holes. So we see that these universes are mutually exclusive. How do they then put together a black hole universe? It's infinite, spatially infinite, and it's eternal, and they stick it into what? Maybe a finite one that's of a finite age. Finite in size, finite in age. It can't possibly match. Whether they stick that into one of their infinite ones. Well, the 2 infinite ones of Big Bangs don't match the infinity of the black hole. They're different because this one doesn't have a K curvature. And it's still eternal. They're Big Bangs that are expanding. They're still a finite age. How much? Still, we're around about 13.8 billion years. They've edged it up from 13.65, and over the years it's got up to 13.7, 13.72, 13.75. Now it's 13.8. They're tweaking all their little bits and pieces. But you see, none of these match. So when anybody says to you, I've got all these black holes floating around in the universe and it's expanding, what are they talking about? Nonsense. Their very definitions, which they forget, exclude this. It's not possible. The theory doesn't allow it. Now, if you don't know which Big Bang you're going to talk about, let's talk about the whole lot at once.
That's what they do. Look, now Lineweaver and Davis wrote an article for the Scientific American. They say this: the idea that the Big Bang was small is misleading. The totality of space could be infinite. So which Big Bang are they talking about? The infinite ones? There are two of them, and they're different. And the finite one? Well, it could be, because the totality could be finite, could be infinite. That means it could be finite. They're giving you three at once. This is not science. This is what we call double talk. Now we come here. Weinberg. Weinberg's at the University of Texas at Austin. He's a Nobel laureate. He says all space in this context may either mean either an infinite universe or all of a finite universe. So he's giving you three Big Bangs at once. Well, you can't have three Big Bang universes at once. Which one do you want? You only live in one universe. Unless, of course, you're Larry Krauss, you have multiple universes called a multiverse. And the Big Bang happened everywhere. In the room in which you are reading this article, in a spot just to the left of Alpha Centauri, everywhere. But the space between the galaxies and us is expanding. Now notice this. Where is a spot next to Alpha Centauri? A spot is pretty small. Bill Gates talked about spots. And where's Alpha Centauri? Well, it's smack bang inside, yes, the galaxy that we live in. But the space between the galaxies and us is expanding. So the Big Bang happened everywhere, but only the space between the galaxies is expanding. The spot next to Alpha Centauri, they're not separating from each other. Why? The Big Bang happened there too, didn't it? Yes, it happened here on my desk. Happened everywhere. But for some reason, we're not allowed to have the space next to the spot, or the spot next to Alpha Centauri expanding. Nothing else is expanding except the space between the galaxies. So they give you a balloon, they blow up a balloon, they put spots all over it and say, look, the balloon is blowing up and the spots are moving apart. But the spots themselves, they don't change their size. Really? If you put spots on a balloon and blow it up, do the spots expand? Yeah, obviously. No, not according to a cosmologist. The galaxies don't expand. Only the space between them. Although their Big Bang happened everywhere, including the spot next to Alpha Centauri in our galaxy. Here is a technical reason why you can't add Big Bangs and black holes. We've already seen you can't because their definitions preclude it. Here's a little bit of mathematical mumbo-jumbo that they violate. General relativity is what's called a nonlinear theory. And this means that the principle of superposition doesn't hold. What does that mean? Well, it means if I've got one mass and I take another mass somewhere and I'm going to stick it together in the universe, I've superposed those masses now together in the universe. I can put in more and more, can I? Well, if you're talking about Newton's universe, you can. Newton doesn't put any limitation on how many masses you can have. And when you look in the sky, you have to have a theory that will allow you to put all those masses in, because there are lots of masses out there. Right? But can you do it with general relativity? No. It's a nonlinear theory. So let's take a specific example. Let X be some black hole universe and Y some Big Bang universe. And let Z be some other black hole universe. Remember, there are 4 types of black hole universes and they're all mutually exclusive. You can't put 2 of them together. Let's have a look at this. X plus Y is not a universe. Why? Because it's a nonlinear system. This is a linear combination. X plus Z is not a universe. So we've got a black hole and a Big Bang. You can't put them together. The theory says you can't. Well, we've seen you can't because the definitions don't allow it either. Well, X plus Y plus Z is not a universe either. They're superposing. But you can't superpose in general relativity because the theory is nonlinear. So the superposition is not allowed. Nonetheless, proponents of black holes and Big Bangs, they take some Big Bang universe, they never tell you which one. Then they take some black holes, and lots of them, and they never tell you which type. Then they superpose the whole lot together in violation of the very structure of the theory that they're using and the very definitions of holes and bangs, and tell you we've got lots of black holes in some non-specific Big Bang universe. Well, this is Tolman. He wrote a book long ago on general relativity, and he tells us this. Well, you'll see that Big Bangs are actually one-mass universes. So you can't even have multiple masses. We can then treat the universe as filled with a continuous distribution of fluid of proper macroscopic density and pressure, and shall feel justified in making this implication since our interest lies in obtaining a general framework for the behaviour of the universe as a whole, on which details of local occurrences could later be superposed. So Tolman's telling us that we can superpose all these things. You can't. The very theory that he's using prevents it. In general relativity, superposition is forbidden. You can't do that. In other words, when I gave you the example of X and Y universes, a black hole and a Big Bang, those two universes pertain to completely separate Einstein field equations, and they have absolutely nothing to do with one another. Why? Because they're very different equations. So you take a solution X for the black hole universe, and you take a solution Y for a Big Bang universe, completely different equations, and then stick them together, maybe with glue. But it doesn't work. It's a nonsense concept because it violates the very theory that they're using. Here's an interesting little argument. Einstein says his principle of equivalence is very important to general relativity. He tells us, I've shortened it because it's very long. All we need to know is this. Let now K be an inertial system. Masses which are sufficiently far from each other and from other bodies are then, with respect to K, free from acceleration. We shall also refer to these masses to a system of coordinates K prime, uniformly accelerated with respect to K. Notice that he's talking about lots of masses. Then he says another way of saying this is that in any sufficiently small region of his space-time, and they can be anywhere, those regions, the laws of special relativity must hold. So we see from both of these 2 points here that each one of them requires the a priori presence of multiple, arbitrarily large, finite masses and some photons to be able to see anything. But where do they come from? All the black hole universes and the Big Bang universe violate this principle. Why? Well, we just saw that the Big Bang universe is a one-mass universe because it's continuous, homogeneous, can't be divided out. You treat it as though it's wholly full or completely filled by a continuous distribution of matter. It doesn't break up because as soon as you break it up, you've got multiple masses and you have no expressions for that. So black hole universes and Big Bang universes violate the very principle of equivalence that Einstein lays down as a basis for his theory. So that doesn't work. Let's consider forces, gravitational forces. If you put 2 balls, solid balls on a strings and hang them from the roof and you hold them still and then you let them go, what happens? Well, we know from the laboratory that they approach one another somehow. Cavendish did experiments like this. He found, yes, they go together somehow. But we find that in general relativity, in Einstein's new theory, gravitation is of a much more fundamental nature. It becomes almost a property of space. Gravitation is thus, properly speaking, not a force in the new theory. This came from Willem de Sitter, a Dutch astronomer who was a contemporary of Einstein. Well, that's true, because in general relativity, gravity is not a force. It's what? The curvature of space-time. So what's happening here is the curvature of the space-time here somehow pulling the curvature of the space-time here so that these two things go together, because we know that that happens in the lab, right? And it's not a force, mind you. When we look at it in the lab, it seems to be some kind of force. But in Einstein's theory, it's not a force, right? So this has no explanation in general relativity. In fact, general relativity can't even account for the presence of 2 masses, and it can't even account for the experimental fact that those 2 masses will approach one another if you release them. You hold them still, then release them, they come together. General relativity cannot even describe it, let alone explain it. And yet, we have general relativity being used to talk about black holes all over the place, in an expanding Big Bang universe, and it can't even deal with 2 masses. This is not a NASA photograph. I know that because it's an artist's impression. I know the artist. It's me. I drew this. You can tell I can't draw. This little astronaut, well, let's have what Hawking tells us. This is called spaghettification. You take a person and you stretch them like this and you turn yourself into a piece of spaghetti. Well, Hawking tells us gravity gets weaker the farther you are from the star. So the gravitational force, yeah, he's invoking forces again. Where did he get those forces from? It's not Einstein. There is no force in gravity in Einstein. This comes from Newton. So now he's mixing Newton's theory with general relativity by invoking the forces. There are no forces in general relativity. And our intrepid astronaut's feet would always be greater than the force on his head. Well, when you look at my little drawing here, is he falling head first or feet first? He could be falling head first. That means this black hole or star might be above his head. Well, he's talking about feet, so we'll put it down here. So he is falling feet first. But you can't tell from the diagram. This is very interesting because every time you see a presentation of black holes and big bangs, they put up little diagrams like this sort of thing, and they put all this sort of double or vague talk in here, and you think, oh, he's falling. Yeah, but which way? We have to be sure. This is a technique that advertising executives often use to sell you things. Put up diagrams and drawings and things, and you get a sort of a subliminal effect. And so since there are no gravitational forces in general relativity, there's no weight. You go to the shop and you buy yourself some apples, right? Remember the old days? I remember the old days because I'm old. Because you used to go to the grocery store and you would have a dish hanging on a spring balance. And you put your apples in there, and the apples would be pulled down on the spring balance. The spring balance stretches, and the indicator goes like that and says, oh, you owe me €5. I don't know, you didn't have euros back then, whatever it was, right? So you paid for your apples. You take the apples out, and the spring balance pulls it back up. The spring balance exerts a force against the thing that's pulling it down. We're talking about forces. Can general relativity do that? No, can't explain it. Has absolutely no way of even describing it. So what's happening in our spring balance and our apples is the curvature of space-time of the spring balance somehow causing the curvature of the space-time of the apples to interact somehow to make the spring stretch so that the indicator works and you can know how much to pay for your apples. It can't do it. So we see that it's all done by invoking Newtonian forces in a clandestine way. You're talking about general relativity, and then you talk about forces of gravity. That's a violation of logical thinking. Here's a little diagram of a black hole to explain to you why it is that a black hole is an infinite universe. It contains only one mass. If there is a mass, we're assuming that there is a mass, the black hole. We'll see later that there is none. But let's assume that there is one. Here's flat or curved space-time. So we see what we mean by asymptotic. You remember this from school. An asymptotic curve. It gets closer and closer. Does it ever touch? Never. Is there any limitation on how far this goes out? No. The word asymptotic means there is no bound. So if you don't have some sort of asymptotic feature here, right, then you don't have a black hole universe because we saw that they're defined as being asymptotically flat or asymptotically curved. So here it is. This goes to infinite curvature. That's an infinite gravity according to Einstein because gravity is space-time curvature. So here, infinite means the gravity must get infinite. Where? At a point. Maybe. We'll see later, it could be something else. So here may be a point. It's asymptotically flat. Yes, all right. As you increase the radial distance away from your singularity, you go asymptotically. Okay, that's good. We've got a pictorial idea of what it is now. We see there's no boundary here, so this describes this illustrates what they're talking about. Let's think of two of them to start with, just two. We put the two together. Here he is to the singularity of a black hole. It doesn't matter what type. I haven't specified what type of black hole here because it pertains to all of them. And this goes to another singularity, infinite curvature again. Well, let's look at black hole number 1. Is that asymptotically flat there? No. Is it asymptotically curved in here? No. And if you go away from this black hole and you encounter this black hole and you come to another, infinite curvature. Infinite curvature is a long way from being asymptotically flat or asymptotically curved. Now let's look at number 2. Well, is this asymptotically flat? No. Is it asymptotically curved? No. And this number 2 encounters an infinite curvature at black hole number 1. So neither of these can be asymptotically anything. Well, we've already seen that the definition of a black hole is asymptotically flat or asymptotically curved. So if you've got two of them, is it possible to have a black hole? No. Is it possible to have two of them together? No. Because this violates the very definition of what the black hole is. So how do they put all these black holes together? Well, according to Daniel Stern, he must be right. He's a NASA scientist. He tells us we've got the black holes cornered. Really? He says, well, they reckon that they found 2.5 million black holes with the NASA WISE survey. So he's got them cornered, all these 2.5 million of them. Well, let's look at this one, lots of black holes. I can't put 2.5 million in there, my box is not big enough. So we'll think about the 2.5 million. Well, let's think of one of them. Here it is, one of them. Each one of these 2.5 million black holes encounters 4,499,999 infinite curvatures all around it. Is that asymptotically flat? Is it asymptotically curved? Not a chance. So this is what? Complete and utter nonsense. Here's another gem. I love this one. I think you'll like it too when I explain it to you. Black hole escape velocity. No proponent of black holes even understands escape velocity. Yeah, they have no idea. Right? Escape velocity is a very simple concept. They don't understand it. Let's think of this. This might be the sun or the earth, say. If you have an escape, if you project an object, maybe a ball or a rocket, with the speed of the escape velocity or escape speed, this thing will get away and it doesn't fall down. But what if you throw a ball up into the air? What do? You throw it up into the air, the ball goes up and it falls down. Why? Because its speed wasn't fast enough. It didn't have the escape speed. Did this leave the earth? Certainly. Did this one leave the earth? Well, it escaped, so it certainly left. This one didn't escape, but it certainly left. It went out, it got to a point where it stopped and it fell back down. We know that every day. According to history, Newton was sitting under a tree and an apple hit him on the head because it fell straight down. Now, let's consider a black hole. We have an event horizon. What do they tell you about an event horizon? They tell you that the escape speed is at the velocity at the event horizon is the speed of light, or maybe even greater than the speed of light. They tell you that the black hole, things go into the black hole, but nothing can come out at all. Well, here, things come out. Yeah? Here, nothing can come out. You go in, when you're in, you can't come out. You can throw a ball here, it won't get there. Nothing can even leave the event horizon. And there are no other bodies present. So what escapes from what? If you've got a one-mass universe, as we've seen with a black hole, how can you get the other mass to be even present to escape from it? You can't. And here, even if there was one, can it escape? If it goes in here, you're in here, can it escape? No, because here, at the event horizon, the speed of light is the escape speed. They say nothing can escape. That's the escape velocity of a black hole. Really? Can anything leave here? No. Did anything leave here? Yes. So this idea here that nothing can even leave violates the concept of escape velocity. Just because you have an escape velocity doesn't mean things can't leave. It means things can leave and fall down, or they can escape depending on their speed when they're at first projected. But here, there is no such thing as escape velocity. But they tell us nonetheless that the black hole has an escape velocity and at the event horizon it's c, the speed of light. Not only that, this is what we find in the dictionary of geophysics, etc. Black hole, a region of space-time from which the escape speed exceeds the velocity of light. They're telling us it's got an escape velocity. We just saw it can't have one. But they're telling us it has one. Here's Hawking. I had already discussed with Roger Penrose the idea of defining a black hole as a set of events from which it is not possible to escape to a large distance. He's talking about escape again. It means that the boundary of the black hole, the event horizon, is formed by rays of light that just fail to get away from the black hole. Instead, they stay forever hovering on the edge of the black hole. What? They stay forever hovering on the edge of the black hole, but the escape speed of the black hole is allegedly what? The speed of light. Well, this is amplified by Professor Joss Bland Hawthorne of the Sydney University. He's at the Institute for Astronomy. He's an astrophysicist. He got on television, Australian National Television. He said this. I really like this one. A black hole is a massive object, and it's something which is so massive that light can't even escape. Now, he's talking about escape again. There is no escape velocity. Some objects are so massive that the escape speed is basically the speed of light. Yeah, a black hole. And therefore, not even light escapes. So black holes are themselves are basically inert, massive, and nothing escapes. Let's have a look at this. He says it's basically the speed of light, and therefore not even light escapes. Well, the speed of light travels at what? The speed of light. He tells us that the escape speed is The speed of light. Then he tells us that even though light is travelling at the speed of light and therefore the escape speed, light can't escape. I wrote to him and I said, can you explain this, what you just said on national television? You know what he said to me? Stop sending me emails. That's his solution to this complete and utter nonsense. Right? But people don't realise what they're being told on television or in books or papers. I like this. This is really nice. Meisner, Thorne and Wheeler, they've had a mention today in some ways. Meisner, Thorne and Wheeler wrote a book on gravitation. It's the size of a telephone book. You can use it as a paperweight or a doorstop, right? But he says here, or they say, one crucial assumption underlies the standard hot Big Bang model, that the universe began in a state of rapid expansion from a very nearly homogeneous isotropic condition of infinite or near infinite density and pressure. Now I ask you, how close to infinite do you have to get to be near infinite? Really? Is it infinity minus 1? Maybe it's infinity plus 1, or infinity minus a billion. This is nonsense. You can't get near infinity, near infinite. Well, not to be outdone, Larry Krauss, the famous Larry Krauss who gets on television all the time, tells everybody everything about Big Bangs, ridicules lots of other people. He tells us, but this is what he did on 18th of February in 2013, last year, on Australian national television again, on a show called Q&A. You can get the transcripts, so you can get it and read it for yourself. But he says this, but it is that, in fact, because of discovering that empty space has energy, it seems quite plausible that our universe may be just one universe in what could be almost an infinite number of universes. And in every universe, the laws of physics are different, and they come into existence when the universe comes into existence. Well, how close to infinity did Larry count to get almost an infinite number? You tell me. Can you count to almost an infinite number? Not a chance. But he's telling television land, all the people in Australia at least, on national television, that he reckons you can get an almost infinite number. They do a lot of magic with these infinities. Here's another one. The work that Roger Penrose and I, this is Hawking speaking, the work that Roger Penrose and I did between 1965 and 1970 showed that according to general relativity, there must be a singularity of infinite density within the black hole. Well, now we come to the question of the singularities. There are two types alleged. One is a point. A point has 0 dimensions. It's a mathematical thing. The other black hole, it's for rotating. So we've got 4 types of black holes. 2 of them are non-rotating, 2 of them are rotating. So we have only 2 types of singularities. A point and the circumference of a circle. I'm not saying a circle. A circle has area. This is the circumference of a circle only. Now you tell me how you get mass into a point or into the circumference of a circle. You cannot. So what do? They say, well, the singularity is volume. That's 0. And we got the mass of the black hole. That's some mass m. Yeah? And we divide by 0 and we get infinity. They do that. They say, you can divide by 0. Well, you know you can't divide by 0. Every schoolboy knows that. Every schoolgirl knows that. And they get infinity. Well, when did infinity become a number? You can't do algebra with it. You can't do arithmetic with it. But they tell us that you get infinity to get an infinite density. So they divide by 0, get infinity, and assign physical properties to it. Well, that's their singularity of their black hole. Now, do they divide by 0? Yes, they do. Because this is from a book on astrophysics by Carolyn Ostley. A non-rotating black hole has a particularly simple structure. At the center is a singularity, a point of 0 volume. Yeah, we divided by 0 according to their rules. And infinite density, where all the black hole's mass is located. Space-time is infinitely curved at the singularity. The black hole singularity is a real physical entity. It is not a mathematical artifact. So they're dividing by 0. Here again, this is from Dodson and Poston, a book on tensor geometry. Once a body of mass, of any mass, of matter, of any mass m lies inside its Schwarzschild radius. That's the event, the so-called radius of the event horizon. It undergoes gravitational collapse and the singularity becomes physical, not a limiting fiction. So it's not elementary calculus where you take a limit. No, you actually divide by 0. Well, that's nonsense. Here is the universe comes from nothing. Hawking tells us at the Big Bang itself, the universe is thought to have had 0 size and to have been infinitely hot. Let's think about that. It's 0 size, but it has infinite hotness. What is there to have infinite hotness? And what is temperature? According to physicists, temperature is all these particles jiggling around. And the more they jiggle, the hotter it is. You put more energy, whatever that is, into it, and it jiggles and jiggles more. This is hotter. Well, if you've got zero size, how do you have space for particles? And where do they jiggle? And if it's infinitely hot, how fast are they jiggling? I don't think Hawking's thinking very clearly when he says this. Here, zero size and infinite hotness. This is a meaningless statement. This is Larry Krauss again, 18th of February 2013, on the same television show. He tells us that there's no real particles, but it actually has properties. But the point is that you can go much further and say there's no space, no time, no universe, and not even any fundamental laws, and it could all spontaneously arise. And it seems to me, if you have no laws, no space, no time, no particles, no radiation, it is a pretty good approximation of nothing. He's telling us that nothing is an approximation, a good one, of nothing. In other words, zero is a good approximation of zero, really. But it all came from nothing, mind you. That's zero. Oh, here's another good one. Again from Larry. He tells us, but I would argue that nothing is a physical quantity. It's the absence of something. I remarked in Albuquerque 2 weeks ago when I gave a talk there, I wondered, does this include the absence of neurons? You know, these are the bits in your brain. He got on television a second time. This is the 27th of May. He loves getting on television and telling his stories. There was nothing there. There was absolutely no space, no time, no matter, no radiation. Space and time themselves popped into existence, which is one of the reasons why it's hard. Someone stopped him talking there, see his little dots. You can see that in the transcript. Someone interjected. But with all of this, and they tell us dark energy, we need dark energy to make the universe expand. Hey, but Hawking tells us in his book, energy cannot be created out of nothing. They've just told us everything came from nothing. But he says, oh, but you can't create energy out of nothing. And they're dark energy. Isn't that energy? Yeah. Well, you can't create that out of nothing, according to Hawking, but they do. Now they talk about numerical methods. They have these magical numerical methods. You can't solve Einstein's field equation for two masses. You can't even write a set of field equations for two masses, let alone more than two. So they say, we'll use numerical methods. And they give you, well, binary black holes. Well, where do they get the binary black holes from? They superposed one black hole into another one. We see you can't do that. Then they say, let's apply numerical methods to these two things we just superposed, which you can't superpose, and we'll get some stuff out of that, and says, we can now find out lots of things about the universe by numerical methods on the two things that we just stuck together that you can't do. So numerical methods on nonsense produces what? More nonsense. Now I'm come to a little bit of technicality here, so please bear with me. These are ugly customers, I know. This is Einstein's field equations. This thing here, let's identify them so that everybody knows what it is and doesn't get confused or afraid. Because it's really simple. This looks really tough, complicated. It's really simple. This thing here is Einstein's tensor, the Einstein tensor. That's its name. We don't have to know what a tensor is. Don't worry about it. This thing here altogether, this is the cosmological constant. And they talk a lot about the cosmological constant. Yeah, we've included it here. And this thing here, this T, this K is just a constant. It's nothing. You know, Y equals 5x. 5's a constant. K is just some constant like that. T is energy momentum tensor. Now we've named the bits. This equation, Einstein's field equation, is no longer confusing. We have a word expression for it now. So we can reduce this, or now that we've identified the parts, let's reduce it to what it means. Space-time curvature, yeah, that's his alleged gravitational field, is matched to the material sources. Why? Because he still has to have mass, or matter, to cause the gravitational field. Otherwise, if you don't have mass and matter, you don't have any gravity. So he says his field equations couple his gravitational field to its sources. Yeah, there it is. Here's the gravitational field with the cosmological constant, and it's coupled to its sources. There's the name of the bits. That's what it does. According to Einstein, everything except his gravitational field is matter. Yeah, radiation, charges, mass, electromagnetic fields. All of this is matter, according to Einstein. So, okay, matter then induces the space-time curvature. He still has to have a cause of his gravity, so that's it. Let's have a look at them. There's the co-equations again, just to remind us of the bits and pieces. And let's compare. He says, well, if you set the cosmological constant to 0 and you set the energy momentum tensor, that's the sources. You take out the sources from the equations, make them 0. His G, That's naught, that's naught. So this becomes G equals naught. But this G thing reduces to even something more simple called the Ricci tensor. So the Einstein tensor becomes a Ricci tensor. Note, but I put it in red, energy momentum tensor equals 0. But he tells us that this describes the gravitational field outside a body. What he took them out with this hand, mathematically, and then he puts the mass back in with the other hand by saying outside a body. So this is a circular argument. Well, here it is, energy momentum tensor. This produces the Schwarzschild solution for a star or a black hole. Now let's go over to this side. T equals 0, material sources are gone again. The lambda, it's not 0, and we get this equation, because that reduces to this, and this thing stays there and it arranges so it comes out like this. Ricci tensor equals a cosmological constant term. Notice again that the energy momentum tensor is 0. Yeah, T's naught. There are no material sources. This one is called de Sitter's empty universe. Why? Because it contains nothing. There's no matter whatsoever. So we see here that according to Einstein, momentum tensor equals 0. That means material sources are both present and absent when energy momentum tensor equals naught. The very same mathematical constraint gives matter and one mass universe and an empty universe. Well, that's not possible. You can't possibly do that. So what's this mean? It means this equation is nonsense. It means this equation is nonsense. Do you have a universe with nothing in it? Look into the sky. Yeah? See this one here? This doesn't mean anything. This contains nothing. This contains nothing. So as I said before, even their black hole solutions don't even contain a mass. It contains nothing. That concludes my little talk on black holes and big bangs. But I want to talk a little bit more about some other things, the cosmic microwave background, because this is now getting a lot of airplay. You have a recent report, BICEP 2's telescope in Antarctica. They found Einstein gravitational waves in polarizations of the cosmic microwave background. No, they haven't. They think they have. It's a figment of their imagination. Let's have a look here of a basis of this. This relates to Kirchhoff's law. In German, I think it's Kirchhoff. Kirchhoff? Yeah. Kirchhoff's law of thermal radiation. He takes a box, he lines it with graphite. He checks the radiation. After a little while, he waits and some radiation comes out. Here he gets this nice little, this sort of expression, nice curve. This is called a spectrum of the frequencies that come out of this radiation. And he calls this a black body. Why? Because it's lined with graphite or soot or lamp black. Yeah? And so he gets this thing here. It's lined with graphite, etc., etc. And you get this black body emission spectrum. Now, the cosmic microwave background is alleged to be a black body spectrum at 2.725 Kelvin. That's just a little bit above absolute zero, right? Black body, remind you. Now, Kirchhoff made the mistake of thinking that he could make a box like this out of anything. It could be made of silver or mirrors or anything. And he would get, if he waited long enough, he would get a black body spectrum. So he made one out of graphite, yeah, he gets this. He made one out of soot, yeah, he gets this. So he makes one out of something else, a reflector, a very reflecting material. So he makes a box like that out of reflecting material, and he waits. He waits, it goes past lunchtime. He's getting hungry. He says, well, it's getting late, I'm hungry, and there's no radiation like this coming out. I wonder how long I've got to wait. So he skips lunch and he waits till dinner time. He gets there. I'm not lambasting Kirchhoff, I'm just illustrating the waiting time. So he waits and waits and waits, but he doesn't get this spectrum. So he scratches his head and thinks, I wonder if I put a little bit of graphite in there, if it will squash up the waiting time. In other words, I wait less. So he takes his little box that's full of all this reflecting material instead of graphite. He puts a bit of charcoal in there, or Planck does. I'm not sure which one of them did. At least one of them did. Certainly Planck did. So they put a bit of charcoal or some graphite in here, and then he waits. All of a sudden, out comes this. He says, look at that. I've got now a black body spectrum. Marvellous. That piece of charcoal I put in there was a catalyst. I don't have to wait so long. What does a catalyst do? It increases or reduces the speed of a chemical reaction, right? So he puts it in there as a catalyst. Instead of waiting past dinner time or 6 months, he waits a few minutes or an hour and he gets a black body spectrum. So he says, this little piece of charcoal, that's a catalyst. No, it's not. As soon as you put the charcoal in there, this is a reflector. But the charcoal is an absorber. The radiation in that box there's radiation emitted by the charcoal. It bounces off all the walls, they're reflectors. It goes back into the charcoal. That's an emitter and absorber. It emits again. After a little while, the interior of the box is dominated by the charcoal. It is not a catalyst. It produces the radiation. So Kirchhoff made a big blunder. That's 150 years ago, in 1860. Right. But all of this time, recently, Professor Pierre-Marie Robertet of Ohio State University in the United States has proven that Kirchhoff's law is false. The radiation that comes out of a cavity also depends on the nature of the material. This is very important for physics. It's at the foundation of quantum mechanics, because when Planck formed an equation for blackbody radiation, he introduced the quantum of energy. But this does not hold. So quantum mechanics, the foundations of quantum mechanics are in big trouble. Much of physics now has to be rethought because Kirchhoff's law is not valid. We see it all hinges on the insertion of a carbon particle. Now, if you take a glass of water and put it in a microwave oven and turn it on, what happens? Right? Does it get hot? Yeah. If you leave it in long enough, does it vaporize? Yes. So I ask you, does the water reflect or absorb the microwaves? It's pretty obvious, isn't it? The water must be absorbing the microwaves. Now we know from physics that a good absorber is a good emitter. That's why carbon and charcoal, graphite, it's a good absorber, it's also a good emitter. So water must also be a good emitter at what? Microwaves. So water absorbs microwaves, we know that from ovens. Anybody who's been in a submarine knows that you can't communicate with microwaves. Why? Because the water absorbs them. You have to use really long radio waves to be able to communicate underwater. Microwaves won't do it because they're attenuated so much in a very short distance underwater. So submariners know this, and anybody who's used a microwave oven knows this. But if you're a cosmologist, you have no idea. Right? They have no idea. Now we look at the Earth. It looks to me there's a lot of water there. And there's a lot of water in the atmosphere too. And all of this water must be emitting microwaves. Right? How does the water emit microwaves? Let's take some molecules, water molecules. It's H2O. These are water molecules. Well, water has a very peculiar character. And one of the things it does, it forms a hydrogen bond. Here's a hydrogen bond with the dots. The hydrogen here, that's bound to this oxygen by a hydroxyl bond, is weakly bound to this one here by a hydrogen bond. So energy that goes into the water can go in here and it can go in there. But this is a really weak bond and this is a very strong bond. So the energy is not distributed evenly. A little bit will go in here because it's such a weak one, and a lot will go in there. So the theory, or rather the theorem of equipartition, which is used in physics all over the place, is also false as a direct result of the invalidity of Kirchhoff's law. Right? So this is very important. So the mechanism by which water emits is the same kind of way as it absorbs. Well, not quite, but the way it can emit is that these go like oscillators. Like if you take two springs, one really stiff and one really weak, and you can put them together and make a straight line, and then you can jiggle them up and down. This soft one will jiggle a lot, and the other one won't jiggle much. It's too strong. So that's the strong part, this one here, and this is this bit here. This can emit, this is the cause of the microwave emissions from water. Now, let's have a look at a raw microwave image of the sky. It's made up of, let's think of transparencies. You know, in the old days you used to take a transparency and put it on a machine and it would project. We take those transparencies and we lay them all together. We've got the galactic foreground. That's in microwaves. It's noisy. Monopole means it's the mean temperature of the universe, they say. And behind the monopole is the dipole. The dipole signal is a signal that's produced by the motion of the satellite because it's around Earth or something, right? And the Earth is moving around the sun, and the sun is moving around the galaxy, and the galaxy is moving with respect to the local group. These motions produce a dipole signal. This is well known. The galactic foreground, that's emitted by the galaxy. The galaxy is the Milky Way. We're in the Milky Way, and we're trying to look out of the Milky Way, through the guts of the Milky Way, into space. So this is noise. We want to get rid of that. We want to get rid of the dipole, and behind it is multipoles, and it's an infinite series because the model, mathematical model that they use here is what's called spherical harmonics, and it's an infinite series. So this is the first component of the spherical harmonic, this is a second, or rather this is a 0, this is 1, this is 2. You get quadrupole, octopole, hexadecapole, and goes on, right? So we see here that the galactic foreground, that's in what? It's in millikelvin, thousandths of a Kelvin. The monopole signal, it's supposed to be isotropic. That means it's the same everywhere. Anisotropic means it's different everywhere. Which way you look, what time of the day, it's different. But if it's isotropic, it doesn't matter where you look or what time, it's the same. And the monopole signal, this is supposed to be the temperature of the universe. The dipole signal is anisotropic and it's noise. We want to get rid of that. It's in millikelvin too. The multipoles, the quadrupole, the octopole, the hexadecapole, and all the rest of them up here, they're in microkelvin or smaller even. So that's a millionth of a Kelvin. Now, balloons and rockets were in Earth's atmosphere. Yeah, there's a lot of water up there, and they're close to the water on the Earth. COBE-Furus, this is a satellite that's launched by NASA to find the monopole, the temperature of the universe, and this COBE-DMR, which is to find all these multipoles, anisotropies they call them. And WMAP was another NASA program to find only anisotropies. They can't do any of this other stuff. It can only find out multipoles. And Planck, the Planck satellite, was to find multipoles, but it could also determine a monopole if they wanted to. Let's have a look at the COBE satellite. Here we see an important thing here. Here is FIRUS, the far infrared absolute spectrophotometer to measure the temperature of the universe. Here's the DMR antennae. These are two antennae to define these are differential microwave radiometers. And here we find a shield. This shield around the instrument, yeah. Why? To protect it from radiation. You don't want radiation that coming from up here, down here rather, and going in here, because it contaminates everything. So we want a shield to block it all. So they put a shield on, but does it block microwaves? No. Their shield does not block microwaves. It could never do that. And it operated from 30 to 3,000 megahertz, or gigahertz. You cannot build a shield to cover that range even. It's impossible. There's no such animal. So they build this shield. It's basically radio frequencies and thermal, but does not include microwaves. Here's its orbit. Here it is here. What's the altitude? 900 kilometers. That's not very far. And the Earth is what? Covered in water. And the atmosphere is covered in water. So there's lots of microwaves coming here. And it has a shield that can't block microwaves. So all the microwaves are coming up from under the Earth, under the satellite. They go up there, they diffract in, and they're getting microwaves from Earth. There's no way they can stop it, right? But they think they measured the temperature of the universe. They actually measured what? Microwaves from water from the Earth. But they think it's cosmic. Here's how it works. Now, the FIRUS is an absolute instrument. This is a bit of a misnomer because it's a comparator. But they call it an absolute one because the sky is compared not to the sky, but to a calibrator. They put on board a calibrator and it's a black body. They made themselves a black body, a Kirchhoff black body. They lined the thing with black stuff and it gets a nice black body curve. And so the idea is take the sky signal and plug it in there and take the signal from your calibrator. You can vary the temperature a little bit of your calibrator and you plug it in there and then you take the difference between the two. And if you get 0, you know that the sky matches this. So you can say, the sky has the same temperature and nature as the calibrator. This is black body, and we set it at a temperature. They set it, they say they got a temperature of 2.725 Kelvin. But, the thing is, if and where the sky matches the onboard calibrator, they call it a null, or 0. If it's a difference of 0, it's a null, or 0. A 0 should occur in the interferogram. What's an interferogram? It's the map of the difference between the sky and the calibrator. Let's have a look at one. Here it is. The COBE-Furus team produces this graph. They say, look at this. The internal reference, that's the calibrator, is set at 2.759 Kelvin. And the sky data is near null. Oh, yeah, it's a nice, there's very little bit there. This is all nice and smooth. And yeah, we've got this. Here's the internal calibrator at 2.771. Sky data goes in and it's off null. Yeah, well, it doesn't match that one. They say it seems to match this one. And look at this. There's a big chunk. There's a big blip here. And here they've got two calibrators, one internal and external. They compare the two. Yeah, there's a big blip. They couldn't get their two calibrators to match. Well, Did they get a null or zero anywhere? The answer is no. See this one here and this one here? The amplitudes of these two graphs have had have been suppressed by a factor of between 3 and 5. So this one here and this one here do not match the scale here. Do they tell you that in their graph? No. How do you know that? You have to be an expert in imaging science to spot it. Who did it? Professor Pierre-Marie Robitaille did that. This comes from Mather and his colleagues. Mather was the principal scientist on the Kobe-Firis. So we see that this and this are not on the same scale as that. If you amplify this 3 to 5 times, is that flat? No way. Did they get a null? No way. And they reported a temperature of what? 2.725. Here they say they got a near null at 2.759, but they didn't get a null at all because this and this are not on the same scales. Right? In 1990, they first reported that they were taking samples between 1 and 2 centimetres to the -1. This is effectively their wavelengths, right? 1 centimetre down to 0.5 millimetres. But after 1990, they stopped reporting. After that report, they stopped reporting all data less than 2 centimetres to the -1. Well, you know, we were talking about the satellite and the diffraction over the shield. The lowest frequencies are the ones that diffract the most. An acoustic engineer will tell you that too. The lowest frequencies of sound are the ones that diffract the most. So they dumped that. Why? They're the ones that are very important because they'll really tell you if you've got diffraction. But they decided, we don't like that data, we'll throw it away. As I said, it's the lower frequencies that do this. Now, everything else that didn't fit their curve, they threw into a thing called the calibration file. Oh, that doesn't fit. We'll calibrate that. So I put it in there. This doesn't fit. We'll calibrate that. So they got rid of this data, then they calibrate everything else, and they get themselves a perfect curve, which they say is this. It matches the Planck black body curve at 2.725 Kelvin perfectly. So much so that the thickness of this line is 400 times greater than our error bars. You know, you have to expand this 400 times to be able to see their little error bar. That's how accurate they say this matches the theory. Where's the data less than 2 centimetres to the -1? It's not there. Is this labelled properly? Let's count. 1, 2, 3, 4. Is this labelled properly? No. This is advertising executives at work. You produce a graph, you put in this sort of thing, you don't say anything about it, people look at it and say, isn't that marvellous? But it's deceptive. Bearing in mind the interferogram, how did they get this perfect curve? And remember, we've already seen that Planck's law and Kirchhoff's law are invalid. So you can't get a black body curve from anything but a solid. How did they get this from space? They didn't. So this graph is totally meaningless for the cosmology. The universe is not in a cavity. So you can't even use thermal emission theory because it all comes from radiation from a cavity. Is the universe in a cavity? Is it in a box? No. You reckon it is in a box? I beg to differ. Here is how the Kobe differential microwave radiometers work. Now, the DMR was a differential instrument. What does that mean? It means you take the sky signal from one antenna and you stick it in here. Then you take the sky from another antenna and you stick it in here. Then you take the difference. And anything that's isotropic, like the monopole signal, right, that's the same everywhere. So it will be the same here and the same here. Now, if you subtract something from itself, what do you get? 0. So if the monopole goes in there and the monopole goes in there, you have no chance of detecting the monopole because when you take the difference, the monopole drops out. And all you're left with is little bits that are different in these two channels. And they're called anisotropies. This is how you get maps of the so-called anisotropies, or the little variations in the cosmic microwave background, by using this kind of thing, a differential instrument. Here is an artist's impression of the monopole signal. This is the whole sky. Well, it's an oval, but that's how the WMAP team and Planck present it, so I do the same. And this is an artist's impression because I drew it. And you see here, everything's nice and smooth. If I take this away from itself, what do I get? 0. That's the monopole signal. It's isotropic. And you can subtract that. Yeah, we saw how you can do that. You just put the signals into the comparator and you take them all apart. Now, here's the dipole signal. This comes from the COBE team. This dipole signal we mentioned before is due to the motion of the satellite against the galaxy, against the galactic group rather, local group. And this varies in time and it varies in direction. So they take a snapshot. Here's one example of the dipole. It changes all the time. Here is one. And when you take a snapshot and we want to get rid of that, the dipole signal is anisotropic. So you can't subtract that out, can you? No. You can't get rid of that. If you subtract signals, you will get this bit left. So how do you get rid of it? You data process it with computers. Here is the map from Smoot, who was a principal scientist on the COBE DMR. Notice this big band here. What do we recognize that as? Well, that's the galactic foreground. Why is it present? Well, it's a big anisotropy. He can't get rid of it because you're all looking through the galaxy. There's a lot of radiation there. This is microwave, right? But this is the anisotropic. So he's data processed out the dipole signal we just looked at. The monopole disappeared because he subtracted it with his instrument, differential instrument. So you're left with anisotropies. But the galactic foreground is a big anisotropy. And how do you get rid of that? Well, you have to data process that out because the galactic foreground can't be removed. So he gets an anisotropy map. He can't get rid of the foreground. This is a big problem with all of these satellites. So he gives you a map. All of these are the wrinkles in space-time. He calls this the wrinkles in the fabric of time. All of these little things here. And this one here, what would be behind that if you could get rid of it, if this is true? Would you expect more little green and blues and white and yellows and things? Yeah. You would expect that. If you could get rid of this, behind all it, you'd have all of this stuff filling the sky, wouldn't you? You would expect that. Yeah. Well, if you can't data process it out, how do you get rid of it? Well, you can use scissors or Photoshop. Here we have another thing. Well, where's the foreground gone? This is not I didn't do this. This came from the scientists. Here you got the anisotropies here. What's this? Did you use scissors or Photoshop? One or the other. So this is what? All this stuff that's supposed to be in here, and you tell us that this is the galactic foreground subtracted. Well, that's not subtracted. That's just nothing. And as I said, he calls this stuff the wrinkles in the fabric of time. Well, here's a really interesting thing. I'll read this out. I have to read this out. This is Smoot. We were confident that the quadrupole... Oh, that's what I should have mentioned to you. He couldn't get the foreground. He couldn't get his anisotropies. He scratched his head. He got rid of the dipole. He got rid of the monopole. He couldn't get rid of the foreground. But he says to himself, the anisotropies should appear now. I've got rid of these two noisy things, other than the foreground. He scratches his head. He says he couldn't figure it out. Why? Well, then he went to the quadrupole. Remember the slides I gave you? It's one behind. It's one behind the dipole. He says, I should have my anisotropy. So he says, we were confident that the quadrupole was real. That's the one behind the dipole. By late January and early February, the results were beginning to gel, but they still did not quite make sense. I tried all kinds of different approaches, plotting data in every format I could think of, including upside down and backwards, just to try a new perspective and hoping for a breakthrough. Then I thought, why not throw out the quadrupole, the thing I'd been searching for all those years, and see if nature put anything else there? Why, I puzzled, did I have to remove the quadrupole to see the wrinkles? So their own theory was telling them, take out the foreground. We couldn't do that. Take out the monopole. Yeah, we can do that. Take out the dipole. Well, we processed that one out. And now nothing's there. We'll remove the quadrupole. And what does he get? All of these anisotropies. Marvellous. We found all the little wrinkles in space-time. What does Robitaille tell us? He analysed all this. What does he tell us? Robitaille is an expert in imaging science. He says this. The answer to this question is one of data processing. When Smoot and his colleagues imposed a systematic removal of signal, they produced a systematic remnant. In essence, the act of removing the quadrupole created the multipoles and the associated systematic anisotropy. Once the quadrupole was removed, the multipoles appear as extremely consistent variations on the maps. And Robitaille adds that apparent anisotropy must not be generated by processing. So in other words, Smoot and his colleagues could not tell the difference between data and data processed spots before their eyes. This is all produced by what? Their data processing. We know in many other areas of imaging science that data processing will produce ghost images. They're not there. He couldn't tell the difference between it. Now, here is L2. The WMAP and Planck satellites, they're orbiting Earth. They're here. Here's L2. This is where Planck and WMAP were located. L2 is how far away? 1.5 million kilometres from Earth. There it is. Yeah? And there's Earth. So it's further away from the Sun than Earth. That's L2. Yeah? Here is how WMAP worked. It's a differential instrument. Remember we put up a simpler diagram? Well, here it is, one of their own diagrams with all their electronic gizmos. Sky goes in here. That's a comparator. It spits out something. The difference between the two. That's how their design of their radiometer. Same thing as what's. Now here's their maps. They sampled at 5 different frequencies. Look at this one. See all that red stuff? That's the galactic foreground. That's pretty dirty. This one too, this one too, this one, these two here have got a lot of noise in them too, but they don't like this one. They don't like that or that either. So what do? Well, the first thing is they have to make a single map out of all of these 5 frequencies. So they superpose them all in a way. And they arbitrarily decide on what weights they'll lend to each of these maps. And what do they decide to do? I don't like that one. I don't like that one either. So they decided, let's go for this one. And so they gave this prominence. And they downplayed all of these. You know, this is mapping by trickery. Then they get this beautiful map. Where's the foreground? They've got rid of it. How do they do it? By data processing. All of these things here, they're the anisotropies. The same things that Smoot got. This is WMAP. What's the alleged signal strength? Well, all of this is microkelvin. That's 1/1,000,000th of a Kelvin. Right? So it's in microkelvins. Microkelvin. But what's the galactic foreground? The galactic foreground is in millikelvin. It's 1,000 times stronger. So we know something about this. If you have a signal that is 1,000 times weaker than the noise, we know from laboratory experience that you cannot remove the noise unless you have one of 2 options. One, you have a priori knowledge of the nature of the source, or 2, you can physically manipulate the source. If you can't do either one of them, you can't get rid of that noise. It's impossible. They say they did it. Well, they did better than any radiometric laboratory in the world can do. With this satellite, they say. That's not a chance. Here's the Planck receiver chain. The sky goes in, and they use as kind of like Furus. They compare. Remember, Furus had a calibrator on board. This one has a load, a reference load, a 4K black body. There's 2 of them. Planck carried 2 4K reference loads. There were 2 kind of detectors, the low frequency instrument and the high frequency instrument. I'll only talk about the low frequency instrument because once we've done that, it's all over. So they take the sky, they put it in here, and they compare it to their 4K reference. That's emitting black body. They made a black body out of black stuff in a box. Then they compare them, they take the difference and they play around with it and they say, well, we got all these anisotropies like WMAP. Let's have a look at their black body comparator. Well, how do you feed the radiation from your black body into the comparator? Well, you have to have a horn to collect it. Just like their antenna or their horn collects from the sky. You've got a big horn, comes in. Well, they use this one. They've got a horn here and the radiation's supposed to come off here. It's supposed to be around about 4K. And it's supposed to be black body because all of this stuff's black. Yeah? So if you've got radiation going into here, you can take that off and stick it into your comparator and compare it to the sky up here somewhere and spit out the answer. Right? Let's have a look at this. Here's your black body reference material inside here, your reference horn. This thing here is an aluminium casing. Yeah? And this here, well, they had a problem. They couldn't keep the black body at 4K because they didn't have any convenient cooling method. So what did they try to do? Well, the high frequency instrument had a shield. And so the high frequency instrument was kept at 4K as well. So they decided, well, we'll keep it at 4K, easy. We'll bolt this against the high frequency shield. That's at 4K. That will keep us in thermal equilibrium and we'll have a 4K box. Yeah, great. So they did that. The trouble is, see these paths here? They did that with steel washers and they put in screws. That's metal. What does that do? That creates a conduction path. Now you have conduction from the black body. This is no longer a black body. Why? Because it cannot emit photons. In fact, it doesn't even have to emit a single photon. All the energy to keep this at temperature can be drained into the shield by conduction. This is not a black body. Both of their black bodies are mounted like this, so they have no black bodies on board. They are effectively getting zero from here, which means that they are getting zero into their horn here and comparing to the sky. And what did they report? We got a really good result. The reason why? They're comparing zero from here to zero from the sky. That's why they got a good match, which means there is no monopole signal. That means there's no cosmic microwave background at L2. This proves it, and they don't even understand that that proves it, and they don't even realize that they've stuffed up because conduction ruins this. Now, that comes straight from the papers, the design papers by the Planck team. I didn't make this up. So they have none. So we're getting close to the end. Without the 4K reference loads, Planck has actually confirmed that there's no monopole at L2. Why is that again? Because their black body is not emitting photons. It's not black body. That means they're getting effectively a 0K signal. There's no signal. Then they compare it to the sky. They get a really good, nice match. Why? Because the sky must be at zero. If they didn't have that, if the sky was at some higher temperature, they would have a really huge offset in their device. They could tell straight away the power levels would go up. They didn't get that. So the only possibility is, since their black bodies are not black bodies, they are comparing 0 to 0. They have proven, without realizing it, that they have no monopole at L2. That means this cosmic microwave background measured by Kobe is not cosmic. It comes from water on the Earth. It's got nothing to do with the universe. It's Earth. And they can't get a black body curve because Kirchhoff's law is now invalid, and space doesn't emit in black body. Gases don't emit. They emit in bands. Gases absorb and emit in bands. You will not get a continuous spectrum from a gas or from space. Right? So there is no cosmic microwave background. That's the history of the Big Bang. Well, we've already seen that general relativity can't manage more than one mass. We've seen that the equations that they compare for black holes and Big Bangs are incompatible. And we've seen that when the energy momentum tensor in Einstein's field equations is zero, there's no matter. He has no set of equations that mean anything. So it's the end of general relativity, and it's also the end of the Big Bang. Right? Now, here's an interesting thing. It's now claimed that the axis of evil, I don't know if you've heard of it, George Bush once said about the axis of evil, that's a different one. Yeah. Bush doesn't know any science, of course. I don't think he even knows English. Anyhow, the axis of evil. It's claimed that the quadrupole, remember Smoot had to remove the quadrupole because he was wondering why he doesn't get inside isotropies. Well, the quadrupole and the octopole of the alleged CMB, the octopole is behind the quadrupole, and then the hexadecapole is behind that one. They say, well, we have a definite alignment with one another, with the ecliptic plane, the dipole, and the equinoxes, so that the Earth is the center of the universe. I'm not kidding you. They're telling us now that we're going back to a geocentric universe. The Earth is not just at the center of the solar system. They're using the CMB to tell us that the Earth is at the center of the universe. Well, really? And what shape is the universe, since it's got a center? Microwave radiation from Earth has nothing to do with cosmology. Cosmology is not even a science, and we do not live in a geocentric universe at all. Thank you very much.